All right, welcome back, guys. This is Ray, and today we're talking about dimensional analysis. Dimensional analysis is an interesting technique of analyzing formulas and values with no units and no numbers. And you're probably asking, wait a second, what do we do when we get rid of all our units and all our numbers? Well, as a simple intuition check, if I ask you, how many meters do you weigh? You know that something's wrong with that statement because meters relates to length and weight relates to weight. You know, usually that would be either kilograms or pounds or some such thing relates to weight. You might not even know exactly, the units for these. You just know that length and weight are not the same and should not be analyzed in the same way. So here's an example of that, of a way that you would formalize this and kind of write it out. If I'm asking for a distance between point A and point B, you know that that's a length. Distance point A to point B. All right, distance, we'll call it D. And whenever you're doing dimensional analysis, you're like putting these brackets around the quantity that you're analyzing. Okay, so D, that relates to a length. And just for convention's sake, we'd like to put a little one, to the first power, so one length. If I ask you how many square feet is your bedroom, you know that it's either a square or a rectangle of some kind. Well, that's two lengths that are going to get multiplied together. It doesn't matter that they're different because we don't care what the numbers are. We just know two lengths. So area, we'll write area in brackets, is a length times a length. So we can write L to the 2. Pretty straightforward. Same thing with a circle. If you've got a circle, radius r, you know that the area of that is pi r squared. Well, like we said, no numbers, no units. Pi is just a number, but r is a value, is a length. And this length is squared. So there you go. Area, length squared. If we go to volume, we're dealing with, imagine I have a friend who's really into fish, and he always talks about how he's getting a bigger fish tank. So there's a fish tank. You know that's a length times a length times a length. Length, width, height, those are all lengths. So that's length, 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 L cubed. So the dimensions of volume are length cubed. The same would be for, instead of a circle, if we're looking at area of a circle, what if we're looking at the volume of a sphere? You might remember volume of a sphere is, the equation for that is 4/3 pi r cubed. In this case, if we were dimensionally analyzing this, we would know, okay, we don't care about the number, don't care about the pi, which is also a number. R cubed becomes length cubed. And so let's show that in a couple problems here, just to kind of drive that point home. All right, so these problems are coming from the physics textbook linked below, so go download it and have a look and have a play with some of these. I'm just going to do A, B, and C here. So a student is trying to remember some formulas from geometry. Maybe you're in geometry now. For me, that was a long time ago. In what follows, assume A is area, V is volume, and all other variables are lengths. So just to write this out again, the dimensions of area are, say it with me, L squared. The dimensions of volume are L cubed. Nice. All right, so we've got those. So we want to know in A, we are looking for something that matches the dimensions of volume, L cubed. So here we go. We've got, they give us V equals pi r squared h. Pi r squared h. You might not even know what this is referring to, what the volume of this thing is. It doesn't matter. We don't even have to know what the shape is in order to analyze it. All we know is we're not going to worry about the pi. We've got r, which we said is a length, squared. So let's put that L squared, and that's going to be multiplied by h, which in this case, they don't say. Usually h is a height. So a height is just another length. And that leaves us with L cubed. And that is exactly what volume should be. In case you're curious, if you look at pi r squared, you know that is the area of a circle. And if you multiply that by a height, you're basically extruding the circle down to get your length and to get your, you've got your area of the circle there. Your pi r squared, I guess in this case they marked it as h. That would be the volume of a cylinder. Fun fact. Let's look at B. Area. Okay, so area. Now we're looking for something that equals L squared. So let's write it out. 2 pi r squared brackets plus 2 pi r h. In this case, we'll write it all out because we want to make sure that these two terms match. So 2 pi, we don't have to worry about that. L squared plus radius is a length, height is a length, length, and so we know that that is length squared. That matches area. Check. And check on this one too. So awesome. That is actually 2 pi r squared is the area of the two ends, the two circles at the ends of the cylinder, and then 2 pi r h is that's the area of the actual face around the circle. Anyways, another fun fact. But we don't even have to know that to do dimensional analysis and know for a fact that we are dealing with area here and volume here, which is what makes it so awesome. All right, let's look at the last one, volume. Again, back to, we're looking for something that's L cubed. 0.5 BH. Okay, they don't say, again, which they should, B is probably the length of a base of something. H is probably the length of the height of something. So we're just going to say, don't care about the numbers. That is an L and an L. L squared. That is not L cubed. So that is not equal to the dimensions of volume. So that would be the way you'd want to write that one out. In case you're wondering, of course, you're all pretty bright, probably a step ahead of me. Triangles, base, height, the area of a triangle, not the volume, is 1/2 base times height. The way I always remember that is if you look at this as half the base and you moved this half of the triangle up over here, you've got a rectangle. That is, the length is 1/2 of the base times the height. Anyways, little tricks. That's how I remember that. You can do D and E. They're exactly the same process as what we just did. Awesome. Okay, let's look at another one. This one, we're just going to deal with a couple physical properties, which is great since this is a physics textbook that we're working with. In this case, they were really nice. They gave you M is a mass, so the dimension for that will be capital M for mass. S is a length. V is length times t to the minus 1, which if you think about it, that would be length over time. That's a speed, right? Miles per hour, meters per second, femtometers per, hours or whatever. Anyways, whatever you're measuring, it's a length over a time. And then length over time squared is an acceleration, time is t. So F equals ma, we're just going to do a couple of these. F equals ma is one of the most beautiful equations in physics, in my opinion. You're going to see that a lot, and you'll probably memorize it. But in this case, if you don't know what F, force, is at this point, you can still dimensionally analyze it to get an idea of what force measures. So we'll put ma there. We know that M is a capital M. That deals with the mass. A deals with L t to the minus 2. Put ones there just to make our teachers happy. And there you go. You got mass times length over time squared. That is the dimension of a force. So a force is effectively how fast can you accelerate a mass, which is ma. So that's a great physics-related quantity. Here's another awesome one. K equals 0.5 or 1/2. I would probably write it just 1/2 mv squared. In this case, it's a lowercase v. That refers to our velocity, not volume, as in the previous one with capital V. So we'll analyze that. Don't care about numbers. We do care about mass. v squared, so let's see, our v is L t to the minus 1. That whole thing is squared, so what do we get? We get m to the 1, L squared, t to the minus 2, and there you go. Awesome. That is actually the dimensions of kinetic energy. So if you got a car that's racing down the highway, if you know the mass of the car, and then you know how fast it's going, miles per hour, meters per second, something like that, then you square the velocity, and then multiply by the mass, divide by 2, and you've got the kinetic energy that car is carrying. The rest are all the same. I'll let you take a whack at those ones. You've got this. And just one more, because every once in a while it gets a little weird, and this is a case where it gets a little weird. This should be theta, but the textbook had problems, but it's open source, so it's still awesome. The arc length of a formula. Okay, arc length means if you have an angle, theta, and this is the portion of a circle subtended by this angle, right? So imagine this circle goes all the way around the page, but we are only looking at the arc length of this portion of the circle. It's a little hard to tell. That's an arc there. I'll try to draw a straight line for comparison. So imagine that there's your point A to point B. A straight line would be that. Your arc length is this. Straight lines, you know, are just a length. Arc lengths are also just a length. But the trick here is, so that's your radius 0, your radius r, your arc length s. What it asks here is, what are the dimensions of s? As I just said, s, dimension, is a length. And then b says, what is r? R is also a length. Because when you calculate this out, you'll get this arc length is some, millimeters or inches or miles, if it's a crop circle, I don't know. But it's just a length. It's a curved length, but it's just a length. So dimensionally, these are the same. What does that mean about theta? That means that the dimensions of theta are 1. They're dimensionless. Angles, remember this, are dimensionless. Now, that might be really confusing. Think about it this way. The angle is just telling you what portion of the circle we're looking at. It's not actually a quantity, it's a ratio. So if you say the diameter of a circle, of an entire circle, what is that? That's 2 pi r, right? 2 pi r. And if you normalize that, what I mean is you divide by the radius itself, because you want to get rid of that radius term. So you imagine a circle of any radius. And we don't want to worry about the actual diameter. We just want to talk about how many times, what the ratio is to go around the circle. You normalize by r. What do you get? You get 2 pi radians. Radians they're kind of a representative unit, but they're dimensionless. They're a dimensionless unit. These come up every once in a while. You deal with dimensionless numbers here and there in physics, and it's to allow you to calculate other things that have actual units and quantities. They're super useful, but they're a little bit confusing in dimensional analysis. Angles are going to be the most common one. So that's why you could consider this as like a length over a length. Put our ones up here. Length over a length equals 1, dimensionless. Just try to explain that, because sometimes it can get a little confusing. All right, best of luck. You guys got this. You're awesome, and I will see you again soon.